Well, lots of stuff in there, but it went very fast, so it's good to go a little bit deeper on
Sure.
it. But my problem with the hypernetworks, the way I've seen you present it a couple of times, is that you say there is an additional structure, but it's not clear what that structure is. You put an array relationship, but then just an ordered list of items. What's the internal structure of that ordered list of items? One list of 4 items in a particular order is not the same as another list of 4 items in a particular order. So it's an additional structure, but you don't know what the additional structure is. So unless you have some way of analyzing that additional structure, I'm not convinced that this is a very useful tool. At least with traditional binary networks, we have some tools that we know that you can send something from a link from one item to another. You can have some kind of a flow, and you know that flows are conserved. You can use lots of other stuff. Well, in this case, I lack a little bit these extra tools to find what is the additional structure. I know there's an additional structure, but just enunciating it doesn't solve the problem. It needs to be analyzed.
Well, there's to answer that question, in the same way that you have tools in network theory to analyze various things, and you have similar kinds of tools in hypernetworks. So that's an obvious generalization. The notion of connectivity, which you compute in a network, you compute the connectivity in hypernetworks. So I think that's not really where your question lies. Your question lies is where are we getting an extra understanding or an extra attraction from this? And the answer is that if you, first of all, it's the algebraic representation, that this representation enables you to do operations on the relations. So that if you've got R1 and R2 interacting, then you need to think about the algebraic relationship between them. So that is, again, necessary if not sufficient to understand complex systems. But also this representation sits very closely alongside implementation in computers. So for complex systems we have to use computers because we have to put the data somewhere, we have to process the data, we can't do the whole thing by hand. Which means that we need data structures that can represent the objects which are important to us. And so what the R's mean, the R1s, the list of vertices is giving you information about those particular things, and the R is doing the computation to find out what's related. That's important. And so I would say that is where we're getting something extra from this. That this is actually supporting new kinds of data structures which we need for computing complex systems. Also, I think it gives you, I think conceptually it helps you in the same way that just the metaphor of the network is useful. I think the metaphor of the hypernetwork is useful as well.
No, I understand the usefulness that if you have more than 2 elements in a relationship, you have the simplices, then you can see how much overlap there is. You can have a 5 simplex and a 4 simplex, and they have 2 vertices that overlap, or they can have 3 vertices that overlap. That gives you an additional structure. But that doesn't seem that much more than what a hypergraph would do. I'm thinking about the example you give about the phone call with 3 people. Yeah, a phone call with 3 people is not the same as 3 phone calls between 2 people. But then, if you go from 3 people to 4 people to 5 people to 6 people, it's just kind of a quantitative addition. It's not that that 6-person phone call is so structurally different from that 5-person phone call. It's just an unstructured group of people who are together in a phone call. So sometimes the additional structure matters, sometimes it doesn't.
Oh, for sure, of course. But when it matters, it matters. Because if you take, in this room we've got 1, 2, 3, 4, 5, 6, so about 10 people. And so we're all part of this meeting. And so even if somebody says nothing in this meeting is, they are absorbing information from this meeting, which is a consequence of the fact we're all here together. So, I mean, this is implicit in Gestalt theory. I mean, the Gestalt is just different from the perception paths.
Yeah, but how is it different? That's unique in each case, and I wonder whether this kind of structures can capture this unique gestalt. Just saying it's different from this.
It could be unique in every case, but in fact what we do when we analyse systems is that we classify things. So we have things which are not identical, which are similar, and from that we get ways of representing it, which is useful. I put this slide back because if you transpose what you said into chemistry, that is, for a chemist, the fact that it's the same set of atoms is clearly not sufficient.
No, I agree.
And I truly believe it's like this in social systems, so that we have relationships. Certainly have pairwise relationships, of course we do, but we have interdimensional relationships. So if you have a family, particularly if you have children, that when you're all together, there is a dynamic which can only happen when you're all together. Which I guess is why we like to have dinner together, because it supports a different kind of dynamic, a different kind of information that can flow. New things can happen. So, I think I don't need to defend the notion of the only relation. I'm sure you're not questioning that. But I think I understand what your criticism is, and I'm sensitive to that, which is what are we getting out of this that's extra, that's useful? And that's the question, which is highly pertinent. And as part of my evangelism, I have to answer that question. So I'm aware of that.
In fact, what you are putting, this extra information is on this R relation. Now, how to express that relation, it's the problem.
Yeah, it's easy to make an array list of things and say the order is important.
But apart from that, the R...
What really is the emergent result?
Methodologically, the point is that R is significant, and can you compute it? And if you can't compute it, do you know what you're talking about? So if you can't compute R, then you're not going to be able to discriminate these two molecules. And if you can't discriminate, what kind of chemistry are you going to have? I'm not sure if I've got this isomer or that isomer, but it doesn't matter because I'm too damn lazy to think about it. I think we have to think about social systems at the micro level. We have to understand how these micro level structures do aggregate. So the example I gave you of the young man whose life was a tragedy. Intuitively, you know all this stuff, you recognise it, and indeed you generalise it. But this is not just a story about one young man. This is a story about a lot of young men worldwide. So we are making that generalisation. The three things: the mother who's a drug addict, the father who's a violent criminal, and the baby. Now that triangle is a very potent piece of structure. The relationship between them is they live in the same apartment. They don't live in different places. That's an important relationship. Can you test that? Yes, you can go and see it. You can go and watch it. Of course, it's difficult collecting that kind of information. But what I'd say is that the symbol R is telling you that you've got to go and look for the R operationally. And if you don't, something very important is missing.
But note that this example, it's actually represented as a binary graph. So we see that there's difference in structure, but that's because there are different connections. There are different vertices with binary connections.
This picture is kind of one of the narratives of chemistry, which you know that this is a two-dimensional picture of a three-dimensional, or four, God knows, n-dimensional thing. So this is a very simplistic story. That the shells interacting and so on, and then we go back to the Higgs boson and the rest of it. But I give this. But in any case, it's interesting. So you're saying that if you're saying that's a network. So it's a binary network. Okay, then the binary network is an object itself. So this binary relation related to that binary relation, so that you get effectively any relations are everywhere.
But I've also asked myself the question, in how far do we need NRE relationships? And there is somewhere a theory in mathematics that you can reduce every NRE relationship to a number of binary relationships.
Yeah, this I think is Peirce who suggested that. That may or may
I don't know whether it's useful to reduce it, but that's what people do in practice because it's easier to work with binary relationships. So I'm not sure whether that is the solution, but that's what everybody does and it works. So what I'm wondering is, if you don't do it and you stick with the NRE relationships, what kind of extra analytical tools do you get that you couldn't get by a combination of binary relationships?
Well, I think you can't escape it. If you've got a set of binary relationships, say 3 or 4 binary, I mean, if you tell me that binary relationships can then be related by binary relations and related by binary relationships, I think that's not the case. Ultimately, you've got these any relations. You cannot escape any relations, like I showed you with the shoes. It may be the case that a lot of relations, it is computationally expedient to calculate it pairwise if you can do it. I believe that's true for many systems. But sometimes, it depends also on your senses and how you observe things. So that I think in some cases, with our senses, the whole notion of gestalt is they're all working together and they all fire together as one kind of observation system. And so, it's interesting to say, if we took our ears and put our ears over there and our eyes over there, if we would appreciate it the same way. In electronics, so electronics is a classic example of networks where you get Kirchhoff's story of electronics. If you look at electronic components, a typical chip will have 4 inputs, 5 inputs, 10 inputs, or whatever, and the chip will act as in my terms, as a hypersimplex. So you've got all the stuff that comes in on the vertices, which are the pins. You've got the stuff that goes on inside, which is the processing. And in electrical engineering, they try to resolve that into pairwise stuff. And to my mind, it's not very successful. It's not elegant, that's for sure.
I mean, your electronic circuit is always made by little wires which are going from one vertex to another vertex.
Except inside the nodes, inside the components.
Physically, there are a lot of coupling that are not parasitic couplings that are not just along the wires. But the question I was asking myself is that when we take a real-life system and we model it, as a network, we actually make huge reductions and simplifications, but we gain a lot of computing capabilities and tweaks and algorithms to do over the simple networks that are made of points and lines connecting between points. If I understand what you suggest is to go from real systems to another kind of modeling, which is much more complex than the networks, where each point is actually made a multidimensional kind of an object, and the relations between objects are like hyperspaces or hyperplanes. So there is a lot more expressive power to the model that you build. But then I'm not convinced, and I'm not sure what is the gain that you gain in being able to manipulate the model and have some useful conclusion towards the real-life system. So this is, for me, the missing link here. Maybe you can give an example of what you can possibly do with hypernetworks that I cannot do with just simple networks. I think this is what Francis was aiming at also. It's not clear. I see the gain in expressive power. It is much more expressive in describing real-life complex systems, but I don't see what you gain in terms of manipulating it and observing things that you cannot easily see in the real-life systems.
I'll come back to your question in a minute, but from there.
I would say modern microcomputers, microprocessors, they are 3 to 4 to 5 billion components. That is not anymore possible to handle it based on conventional networks or graphs. But I'm not sure. Possibly this will direct in this direction. The new needs that these people have to make these concepts more reliable and handleable and tractable. But I'm not sure. 3 to 4 billion components with all interconnections in many, many ways, in many levels, and three-dimensionally, etc., etc. That is incredibly complicated.
But it works. It works.
And on the other side, in practice, it must work. It must work. If not, it is not usable.
Okay, so I'm facing the challenge that there's nothing you can do with hypernetworks that you can't do with networks. Would that be the...
That's the question.
Yes, of course, a very good question. And if that were true, that would be interesting.
If the theorem that n-ary relationships can be reduced to a set of binary relationships applies, then in principle everything you do with hypernetworks can be replaced by a collection of binary networks.
Yeah, you should be careful because that theorem is a mathematical theorem, and mathematical logic. It doesn't necessarily relate to all kind of weird stuff. I think it really comes back to sensors, as I was saying, and this notion of the stuff. So, you know, if you have an n-ary relation, then you maybe have to build a sensor to perceive that n-ary relation. And my point is, if you're not sensitive to the n-ary relation, you won't build the right kind of sensor. So that sensor can be a physical sensor. But actually, as in social systems, we're making instruments to try and observe things. So if we don't design those instruments to observe the n-ary relations, then we won't observe the n-ary relations. I think strangely enough, in vernacular ways, the words we have very nicely handle these very complex n-ary relations. So, you know, in normal language, this is not an issue, really. We know that there are wholes and there are parts, and we've known that for 2,000 to 3,000 years. I take the challenge that you throw down, and so maybe I haven't convinced you that there's something in hypernetworks which network theory can do. I think this, again, that's a question that can be divided into two parts. One is that everything you can do in hypernetworks, you can do in networks, but it's much, much, much more difficult. That's one possibility. It's more complicated, combinatorially, maybe even being practical. The other thing is that there are things you can do with hypernetworks which you simply cannot do with networks, which is my position. So, I'll give you an experiment which is kind of underway that I'm doing. So I've done a lot of work in machine vision, robotics. I've looked at a lot of systems, social systems, physical systems, stuff like that, getting examples of this kind of approach. So in machine vision, you have ultimately you have the lowest level, you have pixels, and the pixels have grayscales and stuff like that. And in machine vision, you're trying to solve the problem. If I take a picture of you people, then I can run some program and tell me that this is a room with people in it and who the people are and stuff like that, and what kind of clothes they're wearing. Machine vision has, I believe, been stuck for a long time because it can't make a big breakthrough. When you, as an engineer, when you make a machine vision system for a particular purpose, so you hack out the code and the system more or less works, and you build a representation of whatever it is that's in the image from your head. So you say that edges are important, these are important, or whatever. That's exactly my notion of the intermediate word problem. So the engineer is is creating the intermediate words. Now, probably or possibly, the engineer is not creating the right intermediate words. So the ontology that's being built for this particular machine vision problem is the wrong one. And certainly it's limited. So if I make a system to recognize car number plates, it's not going to recognize tumors and brains. And it won't adapt itself to do that. So this interests me very much. It would be great to have a machine vision system that could adapt. So say today I'm recognizing number plates, but that's going out of fashion, so I need to do something else, and I'll become something else recognized. And what that means is, in my terms, that machine vision system has got to create its own intermediate words. It's got to create its own constructs. How is it going to do that? So the way I look at this is that those intermediate words are hypersimplices. They're structures. So if you look at pixels, at the low level you've got configurations of pixels. So you've got 4 neighbours or the 8 numbers, and then you create polygons. So you can resolve the polygons into binary pairs, exactly as you say. But actually, the object itself is a set of particular pixels with this relationship on them, and you can classify that. You can make certain kinds of polygons. And so, for a system that's going to build its own intermediate words, it has to be able to make stuff and decide whether this stuff is interesting or not. So, the problem that I've been working on, which interests me a lot, is if I say, so if I give my computer something like this, can my computer learn the difference between them? And so, if I give it one of these, so you see, if I use your intelligent systems, you would probably tell me that this is one of those. At least I hope you would. However, consider a universe in which we have some of these. So, is this one of those? And the point is, it depends what the purpose is. So I can recognize these things. I call this smiley face. And I call this a frowny face. And I call this a square face. And I call this a circular face. And so now I can have smiley squares, frowny squares, etc. And so if I say, for what I'm trying to do in this machine vision system is to recognize smiley faces, then I'm going to aggregate this stuff differently from if I'm interested in square faces. So the machine vision is not prescribed by the system itself. It's prescribed by what I want it to do as a user. So I'm sort of the environment of this system. And so my experiment consists of having a system. Obviously, when you look at the things, you can detect these polygons, and then the polygons have certain properties, and you classify them according to whatever it is. So my machine's got to, first of all, find the polygons, and it's got to find the properties, it's got to decide whether this is important or that's important or whatever. So my experiment is that my system, starting with the basic image, will have some kind of low-level stuff to make bits. But it will put stuff together, and it'll actually ask me, are these things to be considered the same or not? Or are these things useful? And me as the environment, I say yes, in which case the system survives, or I say no, in which case that bit of the system dies. And so my hope is that I can evolve a system which will recognize these faces. So if I'm an environment that likes squares, so I'm looking for squarey faces, then I will give a different set of answers than if I'm an environment that likes frowns or smiles. And so there's an example where my system has to create its own ontology, and my own belief is that intermediate words, these are what I'm calling hypersimplices. And I actually think that taking a network theoretic point of view would simply not be rich enough to do this. Anyway, that's an open-ended challenge. I first of all have to solve this problem my way, and then I can throw it open to say, could you do the same thing with just networks?
Yeah, but these kind of problems are typically solved in two-dimensional vector space, which is much more structured than either binary networks or hypernetworks. So the question is, can you do something with hypernetworks to solve this problem that does not require the whole two-dimensional vector space? That's not obvious, apart from saying, yeah, it's different. These are different gestalts, but you can't say how they are different unless you have the whole two-dimensional vector space to define a square and a circle.
Well, okay, well, you tell me then, how would you represent a gestalt using a network formalism?
One of the things that interests us most, we have been working on, is something called chemical organization theory. And it starts from a formalism which is similar to what I would call directed hypergraphs. You have an input set that is turned into an output set. So it's not like hypergraphs where you have just sets. I agree with hypergraphs are very poor structures.
Well, they're very nice things. So.
Yeah, but what you lose is a directionality.
Right.
In this formalism, it's inspired by chemical reactions. So you have A plus B gives C plus D plus E. Something in that sense. So you have an input set which is turned into an output set. And then you can start analyzing networks of these kind of reactions and find closures in there. Closures meaning that the elements of your network are being reproduced by the network itself. And that is a kind of a gestalt, because it's the equivalent of an autopoietic system. You have a number of input elements that are via a number of intermediate steps turned into themselves. And everything that is in the system is produced by the system. So it's kind of a closed recycling system. That is a gestalt which to me makes sense from an evolutionary point of view. It's a kind of a self-maintaining system. And I think that all gestalts, that's also one of the principles of gestalt psychology, they have some form of closure. Of course, what is closure? There are many definitions of closure, but my general philosophy has always been, if you're looking for something to look at as a gestalt, you need some kind of a closure. And this kind of chemical closure is up to now the best formalism I have found to express lots of different closures in a way that to me makes sense from a dynamic point of view. But I also can't guarantee that I can reproduce all the things you want to reproduce in this formalism.
Well, okay, I mean, I take the challenge to produce an example where you simply can't do it with the network approach. To me, it's kind of perverse, really, to insist on networks when the world so manifestly has interrelations that it's passing, the camels through the eyes of needles to try and do that, because it is, if you take n vertices that have any relation on them, to try to map that into a network, let's say, seems to me perverse. You may be able to do it. In some cases you may not, but to me it is much more natural to have, if you wish to see it's a hypergraph edge or it's a hypersimplex, that is a much more natural representation. I think also, as I said before, that it's important to realise that the symbol R is very, very important, because the challenge is you've got to compute it. You've got to have some operational way of observing things with that relation on them.
My problem still with the R's is that they are tuples, they are just lists of things. There is no internal structure, just a list. That means that the order is important, but it's just a linear order. The simplex looks as if it's more than just a linear order, but the vertex, it doesn't say, you don't really use a geometric structure.
Well, the same is true of an edge in a graph. What I'm saying is that the hypersimplex is a generalization of the nation of graph. What you're doing is you're saying that in fact you want to talk about networks. So you want to say that as you just said, stuff like that. So clearly the network is not a vertex and the network is not an edge.
Let me do what I mean. So a normal binary network is one vertex, one link between two vertices. A hypergraph is a number of vertices and something around it. What interests me is this. And then I can start connecting them, because like that I have both aspects. I have the aspect of having several things at once in a kind of a conjunction or disjunction, and I have the directionality and the linkage.
Okay, well the first thing to say is that you've got some operator here, which is, yeah?
It's not really an operator because it's not a function. It's the simplest kind of link.
So what is your arrow mean?
So it's this. If these are A, B, C, and these are D, E, F, then what it says is A plus B plus C gives D plus E plus F. That's the chemical notation. In a set theory notation, I would have something like A, B, C, D, E, F. This is my minimal element. It's the equivalent of your NRE relation. Your NRE relation would be something like A, B, C, D, E, F.
Well, I'll come back to that. But first of all, I'd say this, that if you put this arrow here, right, what does it mean? It's an operator.
It puts an order in it. It says
it's a symbol.
It's a symbol, but it's a direction. It means there is a directionality. It's not the same going in this direction or in that direction.
Well,
it's a process. It's kind of it's the simplest kind of process.
Well, it's an algebraic object. I mean, within your formalism, it has some properties.
Yeah.
So there's things you can do with the arrows and things you can't do with the arrows. So in your formalism here, your A, B, and C are not arrows. They're different.
No,
things.
they are.
Okay, so I mean, making this out as a formal system, that's a certain kind of object with certain kinds of properties. And I want to give it a symbol F, but I don't mind if we just leave it as an arrow. That's fine by me. But you've got, this is important in your system. So you're saying that there's some relationship expressed by the arrow between this and that. Okay, so I have to call that R, but I don't mind if you don't want to do that. But if that relationship is significant, you need to know about it. What your symbol's doing is it's giving you essentially like a pointer. It's saying this is where it is. This is what you want. Now, to go one step further with this, the deep problem with this is that are you happy to tell me that you've got, for example, A, C, and B goes to D.
Yeah, for me that's equivalent. So the order here is not important, the order here is important. So I have both an ordered and a non-ordered part.
If it's ordered, you can't use the set theoretic notation because by definition, with set...
This is not ordered, this is ordered. So the element has both aspects, an ordered and a non-ordered aspect. While in traditional approaches, either you have a hypergraph and it's not ordered, or you have an NRE relationship and then it's all ordered. So what I want to have both ordered and not ordered.
Well, I think this is a profound disagreement between us because with the set, you cannot discriminate A from B. Because they're elements of the set.
Yeah.
If you want to give them different symbols, you're now creating other kinds of sets. The set is a class of elements. Any one is representative of the set.
The set in this case is implicit. I mean, this is the whole This is the minimal element. This is the minimal element. That means that the set is defined as the input part of this, what I call a reaction. That's a reaction. So this thing does not exist on its own. It exists because there is this reaction. And that gives it certain properties, because I will, of course, not have just one of those, I will have many of those. I will have this hyper network, it's also a hyper network, but in a different meaning, of all these kind of things. And out of that you can get structures, you can get gestalts, you can get all kind of very interesting structures.
But you know, if you do this, you go, okay, now if you change it, and the point being that the set theoretic notation doesn't give you what you want. Now, it's not rocket science just to say, okay, the order's important, in which case you represent it by a simplex, C, which is then not equal to C, A, T.
No, but if you want to have this structure, you could represent it simply by two of those. You could have, no, you had CAD, CAD. So you can have this structure.
Okay, but this is not a set now, this is a structure.
No, but the set is just a generalization of the normal graph. It means you can have more than one input, more than one output. So this is one element, this is one reaction, this is another reaction. These are elements, but they could be sets. An element is a singleton, it's a set with one element. So,
Yeah.
So what I mean is this structure could be put in the same formalism.
Well,
I don't know whether this structure can be put in the formalism.
yeah, of course, you know, if you can transform one formalism to another in a well-defined way, then they're equivalent. That's not a problem. But what I'm saying to you is, if you're using the set theoretic notation as you're doing there, that there are problems because you can. The order is not important.
I know, precisely, because I want to be able to express things that are ordered and things that are not ordered, because the world has both aspects. Some things, the order is important, other things it's not important.
Yeah, if the order is not important, I don't mind. But when the order is important,
You want to be able to express it, that's why you need the arrow. So you have, if you want, you have two operators. You have the plus operator and you have the arrow operator.
well, steady on. Your arrow operator is highly overloaded now because you're using your arrow to represent every binary relation you could possibly have. In this particular case, you're saying that the juxtaposition relation, that this symbol is to the right of that symbol, is what your arrow means. But you're using your arrow to mean different things in different places. And this is really my point, that we need to have a formalism which is clear and precise. And if our formalism allows us to make things which we want to discriminate, then the formalism is letting us down. And the whole point of the hypernetwork formalism, it allows you to discriminate those things that must be discriminated.
Yeah. Usually bus formalisms can be translated to one into the other. The practical question is, how easy is it to analyze a complex system in a particular formalism?
Of course.
Theoretically, you can convert almost anything into anything.
Yeah,
Practically,
we're not arguing formalism
Yeah.
here. That's not interesting. That's like saying expressing it in Dutch is better than doing it in English, or vice versa. Within reason, they're the same. No, that's not the point. The point is that I believe that with hypernetworks we can do things that you cannot do with conventional networks.
yeah, well, that's the question. I'm still not convinced, but yeah, it's difficult to prove.
But methodologically, I mean, God knows we're ignorant enough that we're looking at complex systems which we don't understand. And if your methodology is one that says, I will map this system onto a network theoretic representation, that's a methodological point of view. Personally, I think it's wrong. because I think you should map it onto a hypernetwork theoretic formalism. That I say since our understanding of systems is complex systems is so poor that we're still struggling to understand any kind of system. The systems I showed, particularly the social systems, that hypernetworks is not going to solve those very complex social systems in the near future, and nor is network. So these are kind of open questions.
Which are in the end pragmatic questions.
It seems to me that part of the problem is that if I give simple examples, this will always be the case. If we give toy examples, the simple examples, then you say, well, that's not interesting. I can do that with networks. Maybe you can. So if we take anything really complicated, then we say we can't do anything with it either way. So the question is still open. But I would still stick to my guns. I think that conceptually, that this notion of the whole is incredibly important, and to assert that we can reduce all wholes to binary relations, I don't find that convincing. I think it may be, for many of them, you can computationally.
I mean, I'm not convinced either way. I mean, I don't know whether they can all be reduced to a binary relationship, but I'm also not convinced they can all be reduced to binary relationships. So,
well, what else is left?
yeah, I suspect something else that we haven't yet thought of. I think our mathematics is biased by language, language is a linear medium in which you put one element after another element after another element after another element, and that's exactly what this thing on top does. And binary relationship is just an ordered list of things. And if you make ordered lists of ordered lists, you can express practically anything. That's what language does. But it doesn't mean that the world is made out of ordered lists.
Well, we don't exclusively do that. We use matrices, which are two-dimensional arrays of symbols.
Yeah, which is a step forward, but the world is also not consisting out of matrices. I mean, each formalism is a simplification. And then the question is, it's good to simplify because it's easier to work with. On the other hand, you shouldn't simplify too much because then you become too reductionistic, you leave out important things. So the question is, what kind of simplification do we want to accept? What kind of simplification do we want to abandon and go a level higher? I don't know. I mean,
I think it depends on what you think science is. That science, ultimately equal, is the construction of formalisms to describe what we observe, I suppose. And those formalisms, language of certain kinds with certain grammars and the rest of it. That mathematics itself is a kind of formalism with its own rules and stuff like that. It's a very interesting question. Yeah, what else could we do? But so maybe our science should be like music. We should sing the science rather than have formalism. Maybe that's and understand it in a different kind of way.
Let me maybe formulate it otherwise. I agree with you that the traditional mathematics is not sufficient. Binary relationships like used in complexity science network is not sufficient. I agree with you about that. What I'm not sure about is whether your solution is sufficient.
Oh, okay. Well, that's a big step forward. I'm delighted to hear that. So that's a step in the right direction. Yeah, I would buy that. So maybe my formalism isn't sufficient. Maybe it's not good enough. That's very, very likely. That's what I say. I think this way of thinking is necessary, if not sufficient, for the science that we see. And so, if we can agree that the inner relations is something we need, then for me that's a step forward.
Did you? There was in one place was this expression. You had a list of elements and then this whatever it is operator,
Yeah.
as a part of the structure.
Yeah, I mean, the way I do it, I happen to do it like this. So I say you've got
A, B, C,
and R.
Yes, and you didn't go any further. Was it because you didn't want to go to mathematics, or you just it finishes here? What's
No, of course, there is a whole mathematics of this, that I'm not pushing the mathematics, but
Okay.
this is a formula. So, for example, you've got we know that interactions are important. So if you've got, I'll use Venn diagrams because it's easy, but if you've got two things which are sharing something, then other things you get interaction across that shared face. Now, in my terms, this gives you an immediate question, which is if you've got this thing, intersection, whatever that means, okay, so now, of course, you can do trivial stuff with the algebra, what it actually means. So what I'm saying is that, for example, what is the intersection between you and me? Right? So obviously it's not our physical bodies, but there are a lot of things that we have in common. So, for example, we both speak English, so that's part of our intersection, if you want to define it that way. And so if you've then got something where you've got a set of things which you've got a true linear relation on them, which have their own gestalt, and another thing where they share the vertices, but not necessarily the relation. The question is, in this case, can you have an algebra, or some algebra, where this symbol becomes meaningful? And so, there's a whole load of interest in network theory, most so-called multigraphs, where you're doing exactly that. You've got different relations on the same underlying set. And in graphs, there's no problem because you don't see the problem. But in fact, what you're saying is that if I've got, well, in this case, I've got another R here and another R there. But because you're not considering this to be A, bound up with B, that you're avoiding the problem, there is a profound problem of meaning here, which the Hypernetworks highlight.
Did you say that your formula is somehow related to multi-networks, multigraphs or whatever?
Well, multigraphs are effectively saying that if you've got a graph, say, or a network, I don't care what it is, say for me, but a graph is a set of vertices, a set of edges, right? Like that. This is a definition. And then a network, the edges are oriented. So if you've then got two networks, it's possible that the set of vertices intersects. That's the whole point of these multigraphs. And so you can then you've got relation 1 between A and B, and relation 2 between A and B. So you can have, A is married to B, A goes on holiday with B, A likes B, A doesn't like B, etc. And you have these networks are sort of intersecting each other.
Then there was another thing you mentioned, is that in this R, I'm not sure whether I understood it correctly, but there are the relations between elements are defined, something like that. So it's relations between relations in the graph or in the network. Whatever. Is this?
Well, if you've got a multi-level system, so you take one of these hypersyntheses and you consider it to be an object at a higher level. So in that representation, instead of having all the details, you now just say it's a car. Okay? And then you say my car is related to this car. If you're a traffic engineer, you're looking at the system in that respect, where the cars are interacting, even though you could look at them at lower levels. And so yes, you get relations between relations because the higher level relations are putting relations on the objects which have the other relations in them. And if that's significant, which it is, you need to have an algebra which can kind of capture that and can understand all that. I assert.
gentleman. I was trying to also understand the R in the case with the round face and the square face, and comparing it to chemical organizations, you may actually have a structure that doesn't really look the same, but may actually still create a reaction. And I was like, you can do that with the face as well. If you're asking for the smiley faces, then the square face, one of the two square faces actually is a smiley face.
Yeah.
If you ignore the part. So I was wondering, how do you represent that one R and another R can suddenly be equal enough in that direction?
Yeah, it depends upon the system you're looking at and what you're trying to achieve. That you can give a criterion for these two R's to be identified, and if you change.
But, I mean, you said that you want to give that to a computer, so at a certain moment things need to run. So how do you present that R? Is that like a piece of code that
could be.
That's a if-else kind of structure, or how?
It could be something like that.
I'm trying to grasp it.
Well, the R, in that case, it could well be a function in a computer program.
Okay.
So, and then typically you give it the set of vertices with information about the vertices, and then the R computes and then sends you back something else.
Well, that's okay. So, or an object, right?
And in that particular case, of course, the ordering of what you send to your function is absolutely crucial.
Then I can see it as a representation used to create simulations. Like if you have the R can be an agent, right? I mean, if the whole
the R could be something to do with the internal structure of an agent. Yes, that's right. Or the R could, at a higher level, the R could be a relationship between agents.
Yeah.
A lower level.
Hmm?
Or lower level. Oh, this man.
Well, at low levels, yes. I mean, you could have you can resolve your agents into components and make components into components or whatever.
Yeah.
Have other classifications, and then sometimes these lower level connectivities matter. They have other implications. So, for example, if you take machines, it's like like this projector. So that's got all kinds of subcomponents in it. Now, some low level you might find has got a thing which is used in your telephone and in this blackboard or whatever, and that can matter because then, if those components become short in supply, there's going to be an interaction between these devices, which is not obvious in the first instance. Do you understand? Well, so if I've got a machine, M1, which has this set of components, I use sets because it's easier, and M2, which has this set of components. So these are now sharing this component here, right? So to make this machine here, it actually matters how much that costs, okay? So that has a cost of whatever it does. Now, if you manufacture machine 1, you know nothing about machine 2, okay? And then over in Singapore, they suddenly start making millions of machine 2s, which are selling very well. And so suddenly the demand for this component goes up enormously. And at least in the short term, the price goes up. But unbeknownst to you, because you're connected to that, the price of your components is going up. You don't understand why.
That's happening with a touch screen, right?
I'm sure it happens with lots of things. So, these most of the time the connectivities you don't know about them and they don't have any effect, but sometimes they have profound effects.